Can you hear me? Tithi Gupta, can you hear me?
Good afternoon, sir.
Good afternoon. Anshika Gupta. Anshika Gupta. Can you hear me? Vipin Kumar. Vipin Kumar, can you hear me? Vipin Kumar.
Yes, sir.
आप कौन से सेक्शन में हैं?
Section D, sir.
सेक्शन डी में हैं?
Yes, sir.
कौन से कॉलेज से एडमिशन लिया हुआ है?
Sir, Hindu.
ठीक है। अंशिका गुप्ता। अंशिका गुप्ता। अंशिका गुप्ता। अंशिका गुप्ता। भाई आप लोग मेरी आवाज सुन पा रहे हैं?
यस सर।
Yes, sir.
Yes, sir.
Yes, sir.
तो ये
Yes,
मैं
sir.
जिन जिन लोगों का नाम ले रहा हूं उन्हें क्यों नहीं सुन रहा?
Sir, I don't.
अंशिका गुप्ता।
तो शायद लेफ्ट कर दिया है।
तिथि गुप्ता।
Sir, Tithi Gupta, no such person in the meeting.
नहीं, उसने तिथि गुप्ता के नाम से ज्वाइन किया है
तो
क्लास में।
लेफ्ट कर दिया है।
जी जी जी, वो कुछ लोग क्लास जो इस सेक्शन के नहीं है वो एंटर करने की कोशिश कर रहे हैं। एक्चुअली में जिन लोगों को मैंने क्लासरूम से लिंक दिया हुआ है उनका कोई प्रॉब्लम नहीं है, वो तो ज्वाइन कर जाते हैं, बाकी को परमिशन मांगनी पड़ती है ना। निखिल गुप्ता अभी अभी आपने ज्वाइन किया है। निखिल गुप्ता। निखिल गुप्ता। आई एम आस्किंग टू निखिल गुप्ता। निखिल गुप्ता।
सर ये दूसरे सेक्शंस के हैं।
लगता तो ऐसा ही है क्योंकि मेरे पास जो लिस्ट है उसमें तो इन लोगों का नाम नहीं है। तो कुछ लोग दूसरे सेक्शन से घुसने की कोशिश कर रहे हैं। वो
जब आपने नाम लिया तभी ये लोग लेफ्ट कर गए।
वो करना ही था इन्होंने। एक्चुअली में परमिशन ही अलोक उन लोगों को मांगनी पड़ रही है मेरे से जिन लोगों को मैंने जो है क्लासरूम के थ्रू ज्वाइन नहीं कराया हुआ। योगेश शर्मा। योगेश शर्मा। जी हाँ, आपने अभी अभी ज्वाइन किया योगेश शर्मा। डू यू बिलोंग टू दिस सेक्शन? योगेश शर्मा। जी हाँ, योगेश शर्मा। जी हाँ, क्या आप इस सेक्शन में हैं? योगेश शर्मा। योगेश शर्मा। डू यू बिलोंग टू सेक्शन डी? योगेश शर्मा। योगेश शर्मा, कैन यू हियर मी? योगेश शर्मा, कैन यू हियर मी? Class, can you hear me? Bhumika, can you hear me?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
तो ये
Yes, sir.
योगेश, मिस्टर योगेश शर्मा, मुझे नहीं सुन पा रहे हैं आप?
Yes, sir.
सुन पा रहे हैं मिस्टर योगेश शर्मा?
Yes, sir.
आप मुझे सुन पा रहे हैं?
Sir, there is a problem in my mobile, so
कोई
voice
बात
is.
नहीं। क्या आप कौन से सेक्शन में हैं? योगेश, आप कौन से सेक्शन में हैं? योगेश, you belong to which section? He has left. क्लास, मेरी रिक्वेस्ट है, अगर आप में से कोई और भी सेक्शन डी ऐसा है जो सेक्शन डी से बिलोंग नहीं करता है, आई रिक्वेस्ट टू प्लीज लिव दिस क्लास। अदरवाइज मेरे पास आप सबका जो है यहाँ स्क्रॉलिंग रिकॉर्डेड आता है, पूरा का पूरा जो है आप लोगों का कितने पार्टिसिपेंट्स हैं, मैं आसानी से लिस्ट से लोकेट करके एंड आई कैन राइट इट टू द डिपार्टमेंट कि ये लोग मेरे सेक्शन में इंट्रूड कर रहे हैं। क्लास, ये अच्छा नहीं मानते हम लोग कि बिना परमिशन के आप पूछते हैं। पहले एक शिष्टाचार ये होता है कि सर क्या हम आपकी क्लास में आ सकते हैं, फिर अगर टीचर अलाउ करे ओके कोई बात नहीं आ जाइए, तब आप आइए। आप जो है वो क्योंकि हम ऑनलाइन इंटरेक्ट कर रहे हैं और मैं जो है दैट वे इतना स्ट्रिक्ट नहीं हूँ, तो वो इस ढंग से इंक्लूड करना क्लास में इज नॉट गुड। जो सेक्शन आपको असाइंड है प्लीज वहाँ क्लास अटेंड कीजिए। अच्छा नहीं लगता वहाँ टीचर से कोई दिक्कत है आप उनसे बात कीजिए। तो ये मतलब इट्स नॉट अ गुड प्रैक्टिस। किसी को भी टीचर को अच्छा नहीं लगता इस तरह से कि भाई उनकी क्लास में दूसरे सेक्शन के बच्चे आए, और या दूसरे टीचर को भी अच्छा नहीं लगेगा कि उनके बच्चे दूसरे टीचर की क्लास में जा रहे हैं। ओके क्योंकि मैं पिछले कई बार से इस तरह की चीज नोटिस कर रहा था लेकिन एड्रेस नहीं कर पाता था। होता यही है कि आप उसे एड्रेस करने लगेंगे तो आपका कीमती वक्त बेकार होता है, जैसे कि अभी आज हमारे कुछ 1 मिनट वेस्ट हो गए। ओके क्लास, देन मे बी वी कैन स्टार्ट नाउ। ओके सो क्लास, अगर आप ओके क्लास स्क्रीन देख पा रहे हैं आप लोग?
Yes, sir.
ओके सो क्लास, आपको स्क्रीन देखकर ध्यान आ गया होगा कि कॉची इंटीग्रल फार्मूला मैं आपको करा चुका हूं। अच्छा ओके सॉरी, कॉची इंटीग्रल फार्मूले पर बाद में बात करेंगे। या क्लास, लास्ट टाइम मैंने आपको ये थ्योरम कराई थी, बहुत बढ़िया थ्योरम है। अगर f कोई एनालिटिक फंक्शन है किसी बॉल के ऊपर तो हम उसके लिए पावर सीरीज लिख सकते हैं। उस पावर सीरीज का रेडियस ऑफ कन्वर्जेंस कम से कम r तो होगा ही, हमने ये देखा था, मिनिमम r होगा। उसके सीरीज के जो कोएफिशिएंट्स हैं वो कोएफिशिएंट्स भी f की हेल्प से डिटरमिन होते हैं। तो क्लास में इस थ्योरम पर एक छोटा सा रिमार्क आपको दे रहा हूं, उसके बाद हम आगे बढ़ जाएंगे। देखिए सपोज डियर क्लास, f is analytic on this ball which is centered at 0 and having radius r. Class, as I told you, if you remember that any ball which is centered at A and having radius r can be thought of that as if the ball centered at origin and with radius 1 has been dilated first and then followed by translation. So that's why I am considering this ball at the origin. Of course, I am taking radius r. You could even take radius 1. But for me, the radius r is more informative, taking radius r. This is any real number bigger than 0. Class, then, by theorem 2.8, the theorem which we did last time, this one. This was theorem 2.8 at page 72 of your book, J.B. Conway. And then, class, according to this theorem, we can write power series expansion. And this time the power series expansion will look like this. For all z such that mod z is less than r. I hope, class, you must be understanding. The only difference is that this time I have taken a is equal to 0. Is this okay, class?
Yes, sir.
Right? Now, class, if you take an observation, don't you think that it is, I mean, it is something like this. You take a note. If you write this series in elaborated form, this is this. And if you notice, it is nothing but just a polynomial in Z of how much degree?
N.
Of how much degree?
Infinite.
Finite.
Of infinite degree. Bilkul, good. So, class, you know that from your undergraduate course on complex analysis, you know that every polynomial function is differentiable, right? Moreover, analytic, moreover, entire is differentiable on the whole complex plane. So, class, it means this polynomial will also satisfy that property.
Yes, sir.
It is just a polynomial, and because it is of infinite degree, how many times you can differentiate it?
Infinite times.
Infinitely.
As many times as you want, right? As many times as you want, right? So this implies, I can say, and now this polynomial is representing f. So what I can say that f is infinitely,
Differentiable function.
yeah, is infinitely differentiable on the ball this. सो क्लास, एक बड़ी इंपॉर्टेंट इंफॉर्मेशन हमें मिल जाती है जिसको कि आप अपने किसी किसी कोर्स में या आगे चल करके एक कॉमन नोशन होगी दैट एफ बिलोंग्स टू सी इंफिनिटी because differentiable function is automatically continuous, so C stands for continuous, and infinite means it is continuously differentiable. It is infinite number of times differentiable. So every analytic function is, in fact, if I say by a rough language, then I can just say that an analytic function is infinitely differentiable. Of course, when we say this is understood that we are talking in some domain. So this is a very important remark. Every analytic function is infinitely differentiable. Please, class, take a note. This kind of thing does not hold good in the frame of real valued functions. You may have a real valued function which is differentiable once, twice, but is not differentiable thrice. But if you have an analytic function means continuously differentiable. A function which is differentiable once and its derivative is continuous. So if it is so, then this remark says, then it will be differentiable 2 times, 3 times, 4 times, and so on. It will be, in fact, infinitely differentiable. But this kind of phenomena does not happen in the case of real valued function. So this is a very important remark. Okay, class. I mean, you can take it as your homework. For example, you can take it as your homework if you wish. To write an example of a real valued function f so that f dash exists, f dash is continuous, it means f is
Continuously differentiable.
yeah, yes, continuously differentiable हम इसे कहते हैं. But f double dash does not exist. So real valued functions में तो मामला बहुत ही वीक होता है. Okay, good enough class. So class अब मैं आपको जो last time theorem कराई है, based upon that theorem I am going to do some consequences of that theorem, and in that direction the very first consequence is the following. Sorry. Consequences of the last theorem. That was actually theorem 2.8 at page 72 from your book, which we did last time. Some of its consequences. One consequence is the following result. Thus let f be an analytic function in an open set G. Let this be an open ball containing G. Let gamma be this set. I hope you can understand this, that in fact we are having this kind of situation. We are in complex plane, number one. We are having G. We are having a ball. Sorry. We are having this ball with center A, radius R. This is ball BAR, right? And in fact, gamma is its boundary. This boundary is gamma. Is this okay, class?
Yes, sir.
Right? Okay. Good enough. Class. So if we have all this, then the result says that the nth derivative of f at a can be determined like this: n factorial divided by 2 pi I integral over gamma f of w dw w minus a to the power n plus 1. So in fact, class, again I would say that you can interpret this formula from left to right as well as from right to left. It means if I call it its left hand side, if I call it its right hand side, so left to right and right to left means if you know the right hand side, you can determine left hand side, and if you know left hand side, then you can determine right hand side. then in that situation, or you can write then the right hand side as, I hope you must be remembering the interpretation which I gave you for Cauchy integral formula. That was very important, and this will be 2 pi I into this divided by n factorial. It means you can determine the value of this integral. So this is the meaning of interpretation from left to right and right to left. Is this okay, class?
Yes, sir.
So let's see the proof. Proof is very easy. Now by the theorem, for all z in the ball P A R, we have this power series representation for the function, where how these coefficients are given. These coefficients are given as this. Is this okay, class? This
Yes, sir.
this we know by the theorem, right? So class, let me call it number 1, this expression. Also, during the proof
एक्सक्यूज मी सर
of the, yes,
सर जो आपने ऊपर फॉर्मूला लिखा है वो सर्कल के अंदर के हर पॉइंट के लिए ट्रू है ना?
ये फार्मूला,
यस सर।
मैं सिर्फ इतना जानना चाहता हूँ, मैं तुम्हें क्लैरिटी देने के लिए कि यहाँ दो तरीके के दो नोटेशंस यूज की गई हैं, एक नोटेशन ए और एक डब्ल्यू। इन दोनों में से तुम सर्कल के अंदर कौन सा पॉइंट समझ रहे हो?
सर ए है सर्कल के अंदर तो।
यस, बिल्कुल ठीक है, ये सर्कल के अंदर के हर एक पॉइंट ए के लिए ट्रू है, बिल्कुल ठीक है। तो ये डाउट अचानक से क्यों आया? कॉची इंटीग्रल फार्मूले में तो बिल्कुल अच्छे से समझाया था।
सर यहाँ पे आपने जो ड्रॉ करा है ना वो सेंटर को मेरे को लगा कि सेंटर ए है, तो बस सेंटर वाले के लिए ही होगा।
ओके ओके ओके, सॉरी सॉरी सॉरी, नहीं ऐसा नहीं है। कॉची इंटीग्रल फार्मूला नहीं, ये कंफ्यूजन क्यों?
यस सर, आई नो कि वो
Do you remember that? Yes. No, don't get confused, please. ठीक है. If you remember this Z, so if you take A, so this Z was any Z. Do you remember this?
यस सर।
Right. Is this okay? So right. So in particular, if you take Z is equal to A,
यस सर।
is this okay?
यस सर, ओके।
Because when we say this is less than R, it means this is greater than equal to 0. Please take a note. I never excluded the center. It is actually the neighborhood of A, not the deleted neighborhood. So if equality is permitted here, it means Z can take value A. Is this okay? In this formula, Z can take value A. Is this okay?
ओके सर।
ठीक है? Okay, good enough. कंफ्यूज नहीं होना है। चलिए, कहाँ थे हम थे कहाँ? हम कर क्या रहे थे? ओह सॉरी, हाँ हम यहाँ थे। So then during the sorry class, just a minute. Just a minute, class. Then during the proof of the theorem, we obtained, see class, what we obtained. During the proof of the theorem, we obtained the following. Class, this formula number 5 we obtained, right? Is this okay, class?
Yes, sir.
Yes.
So I am writing this. We obtained an is equal to 1 upon 2 pi I gamma f w dw w minus a to the power n plus 1. Let me call it 2. At class, combining 1 and 2 gives the result. Is this okay class? शायद आपको दिख भी गया होगा,
Yes, sir.
है ना? तो दोनों को बस कंबाइन कर दीजिए, दोनों से a n की वैल्यू को बराबर रख दीजिए. Easy. Now class, next consequence. Next. Okay class. Now you will see the consequence of this result which we have just done. So the next result says that let f, so this is contained in some set G, of course, into this be an analytic function. This is analytic, and you are also given that, sorry, why is it happening so? And let mod of fz is less than equal to m uh, for all z in bar. It means what I am trying to say is that there exists some capital M greater than 0. It is given to you. It is given to you, right? So in a way, what I am saying is that function f is bounded, right class? Is this okay class?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So the result says that the nth derivative of f at a will be less than equal to m n factorial divided by r to the power n, and this will be for all n equal to 0, 1, 2, 3, dot, 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 dot. So this is giving us an idea about the fact that derivatives of all orders of f will be bounded at a. Okay. Proof. C class. Class, let this be arbitrary. So class, we have chosen some small r, which is smaller than this given big R, and the choice of this small r is arbitrary. It means we are covering all possible values from 0 to capital R. It means class, the situation is something like this. So suppose I have this ball. This is center A and its radius is R. So once I am taking small r somewhere here, and suppose I take some ball here. So class, you can see that if I take r to be arbitrary in between 0 and r, then I can consider different values for small r, and so you will be having rings like this again and again. And if you put up all these rings, so what will happen class? Ultimately, we will be able to cover up the whole interior portion of the open ball. Is it okay class?
Yes, sir.
Yes, sir. Yes, sir.
By changing the values of small r ranging from 0 to small r, oh sorry, capital R. So this is exactly what I'm going to do. So just go on changing the value of small r, so this whole interior portion will be covered. This is what I'm going to do. Okay. and class let gamma be such that, sorry, or and such that, so you can see that I have taken the corresponding circle. Gamma is nothing but that circle centered at the origin, and ham being radius small r. So class, let me denote it by W. So in a way I can say that gamma is nothing but class. Gamma is in fact nothing but the collection of all those W's in the complex plane such that W minus A is equal to R. Is this okay, class? They are one and the same thing. Is this okay?
Yes, sir.
Yes, sir.
Then by the above result, we have, yeah, is this okay? Right, okay. So by the above result, we have following. The conditions of above result, we have the conditions. So I can write this straightforward. Now therefore, we are interested in the modulus of this. So let me start with it. So this will be equal to the modulus of this expression. Simple algebra. Sorry. And you know that class, you can take modulus inside the integral sign. You will be left with 2 pi I here, gamma, and you will have modulus of this divided by modulus of this and this. Is this okay, class? Less than equal to. Is this okay, class?
It will be 2 pi na,
Yes.
and
G?
factorial of
2 pi.
Yes, you are right. You are right. Modulus of I is 1. Thank you. Yes, you are right. Thank you. So, class, now you know that it has been given to us that in this ball, function is satisfying this condition. So class, take a note. The ball which I have taken with the circle which I have taken with the small radius r is very much inside this ball. It means at every point of this circle, class, if I call it condition 1, so at every point of this gamma, condition 1 will hold, class, for every point of gamma, right?
yes, sir.
Right. So now where this W is, this W is on this gamma. So certainly that condition 1 will hold, and according to that, this thing will be less than equal to M. Is this okay, class?
M.
Right. And secondly, class, these W's are on this. So if these W's are on this, then it means these W's are satisfying this condition, class. Yes.
Yes, sir.
So class, I can write further that this is equal to n factorial upon 2 pi, less than equal to, this will be less than equal to M, and because mod of W minus A is just small r, so in the denominator we will have r to the power n plus 1. This less than equal to is because of that condition, class. Is this okay?
Okay.
And class, you know the meaning of this integral. This integral means simply the length of this curve. Yes or no, class?
Yes, sir.
Yes,
Yes.
sir.
So it, because you are moving W's along this curve, so it means length of this curve, and which is nothing but, class, 2 pi
2 pi r.
2 pi r. And this will be, class, equal to 1 power, r will cancel this 1 power, and likewise 2 pi will cancel 2 pi, and you are left with M, sorry, you are left with m into n factorial divided by r to the power n. Is this okay, class?
Yes, sir.
Yes, sir.
And now, class, as I explained you, that this small r in between 0 and capital R was arbitrary. So what I can do is I can start taking this small r with a smaller value and go on increasing it and go on increasing it. If I go on increasing this small r, and how I go on increasing it, I go on increasing it, taking it to capital R, so that the complete ball BAR will be covered. Is this okay, class?
Yes, sir.
Right? Because we are to make our study at this ball. So now this way I am going to cover this ball. So first of all I write this, that is just concluding it, that is this is less than equal to m n factorial upon r to the power n, and this is for all n 0 1 2 and so on and so forth, right? And now class, letting, because the choice of this r, remember the choice of this r in between capital R and 0, this choice were arbitrary, right, class? Right? So letting small r tend to capital R, right? We have, so class, you can see that in this expression, this small r is involved at only 1 point. And moreover, this expression which involves r is r to the power n, and class, this is a continuous expression, a continuous function of r if you take r as variable, right? And so you can take limit inside. Is this okay, class? So what you will have? You will have this less than equal to m n factorial upon. Is this okay, class?
Yes, sir.
And this is exactly what we wanted. So this result tells us about the bounds of the derivatives, about the bounds on the derivatives of the function. So you can see that this bound is depending upon n. Is this okay, class? So if you take derivative of different order, then accordingly there will be some change in the bound. Okay, good enough. Now, class, the next result is again a consequence of the theorem which we did last time, that is theorem 2.8. So another consequence, and this consequence is very often called as the elementary version of Cauchy's theorem. So what's that, class? It says that let f be a function defined on this into C, and this is analytic, and gamma be a closed. Take a note, closed. You know the meaning of closed. Rectifiable as well. You know the meaning of rectifiable as well. Curve in BAR. So in this ball, you have a closed rectifiable curve. Then the result is very simple. Then the value of integral of f on this gamma will be 0. The result says this. So let us write its proof. Class, let me tell you. Okay, it's okay. Leave it. So now, since so class, clearly we can apply the theorem. As you can see that f has been given to be analytic on this, right, class?
Yes, sir.
Right? So by the theorem 2.8 we have, so we can talk of a power series expansion of f for all z such that z minus a is less than r. This condition basically means class for all those z which are inside the ball. Is this okay, class?
Yes, sir.
Yeah, they're one and the same thing. Okay. So class, if you recall, we have this, and moreover, in that theorem we learned that, moreover, if I call it 1, we learned that the radius of convergence of the series in 1 would be minimum capital R. In 1 would be minimum capital R means would be greater than equal to capital R. That at least R would be its radius of convergence, and it can even be bigger than it. So what I am going to do is, class, so let us assume R1 greater than equal to R be its radius of convergence. So let's assume this. The theorem gives us the guarantee for the same, be its radius of. So the theorem gives us guarantee for it. Okay, class. Class, now let us consider this, class. You consider this. Class, this I have already explained you that every infinite series, now you read this expression from right to left. So what is right? Right is a power series, class, and reading right to left means, so you have power series, and class, you know that power series, you can read it like a function, and it will be an analytic function. This I have already told you that every power series represents an analytic function. Yes or no, class?
Yes, sir.
Yes, sir.
Yes.
Theorem 2.8 says that for every analytic function we can write down a power series expansion. But this I have already told you that every power series represents an analytic function. This I had told you even before that. Okay, good enough. So suppose we consider this power series given by 2, and suppose it represents this function capital Fz. And suppose, class, this is power series, so it will be having some radius of convergence, because only then and then this function will make sense, or the function makes sense only within the portion where this series is convergent. So let's assume alpha to be its radius of convergence. So suppose it has alpha radius of convergence. So within its radius of convergence, everything will be okay. It means within its radius of convergence means what I am saying, class, that whenever z is such that mod of z minus a is less than alpha, for all those z, this expression number 2 will make sense. Is this okay, class?
Yes, sir.
Right?
Yes, sir.
Okay, fine. This is exactly
Yes,
what
sir.
I meant to say. So suppose alpha is its radius of convergence. Now see, class. Now by definition of the radius of convergence, we have, so class, by definition of radius of convergence, 1 upon alpha should be what, class? It should be limit n tending to infinity supremum of, you know, it will be mod of an upon mod of an plus 1, right, class?
Yes, sir.
Yes, sir.
Right? So, and this will be, or you can write it mod of an to the power 1 upon n. You can use that formula also. So in this case, mod of an means class, this is the coefficient. Yes or no, class?
Yes,
Yes,
sir.
sir.
We will have mod of n divided by n plus 1 and its power 1. So by definition, this is the radius of convergence of this series. And class, this is equal to limit n tending to infinity supremum of mod n to the power 1 upon n into. And class, if you have a look at this denominator and you take limit n tend to infinity, so class, you know that this limit will come out to be 1. Is this okay, class? You know this. Because,
sir.
yeah, because all of you know that the limiting value of this denominator comes out to be 1. So 1 upon 1, it will lead to 1. And class, if you recall the definition of radius of convergence, don't you think, please have a look at 1. Have a look at 1. These are the coefficients of 1. So if its radius of convergence is R1, don't you think that this is nothing but equal to 1 upon R1? If you look at the definition of radius of convergence of series 1.
Yes, sir.
Yes, sir.
Yeah. So class, this implies alpha is coming out to be same as R1. Is this okay, class?
Yes, sir.
Yeah, that is the series in 2. Series in 2 means this one is having the same radius of convergence as 1. Good enough, class. And it means what, class? It means, and if you notice, class, R1 we took bigger than greater than equal to R. Yes or no, class?
Yes,
Yes,
sir.
sir.
It
Yes, sir.
means suppose this is R1, so BAR will be somewhere here, class. This will be BAR because R1 is greater than equal to R. So if it is equal, then R1 and R will become same. Otherwise, you will have a bigger set. Is this okay, class? It means, class, if radius of convergence is of the series 2 is bigger than R, then certainly in this portion, that series is well defined. Is this okay, class?
Yes, sir.
Right? And if that is well defined, it means, class, this function is well defined. So basically, claiming this thing allows me, thus, the function fz is well defined in this ball. Because the function f defined, because the series with the help of which function f is defined, the radius of convergence of that series is coming out to be bigger than this number r. So it means within this portion, the series makes sense. The series is convergent, and it means the function capital F makes sense. It's well defined. Is this okay, class?
Yes, sir.
And if this is okay, class, then you observe the following. Observe that f dash z is coming out to be equal to small fz. Can you see this, class? I think easily, because you know that you can differentiate it term by term, because you know that a series within its radius of convergence is
Yes,
uniformly convergent.
sir.
And class, you know that a uniformly convergent series can be differentiated term by term. So if you differentiate number 2 once, let us say, then class, don't you see that it will give you 1?
Yes, sir.
It's obvious, right, class? Is this okay, class?
Yes.
Okay, good enough. Please don't bother about the
Yes,
constant.
sir.
Please don't bother about the constant term. Just manage that. We don't bother about the constant term. Okay, so f dash z will come out to be equal to z. So it means what class? That is, आप समझ गए होंगे. That is f is the function f is primitive of f. Is this okay, class?
Yes, sir.
And now I am going to make use of the fundamental theorem class. So therefore, this integral will be what class? This will be the value of f at z1 minus f of value of f at z2, assuming that z1 is initial point of the curve gamma and z2 is the initial point of gamma. So this you are able to apply because you have assumed gamma to be rectifiable. Now let us use the fact that gamma is closed, and because gamma is closed class, z1 will be same as
Z2.
That too.
yeah,
0.
terminal point. Yes, very good.
Terminal point, yes.
These two will be same, initial and terminal point, because the curve is being given close to us, and hence done class. Is this okay?
Yes, sir.
Yes, sir.
Good enough. So we have seen class that if we have a function small f which is analytic on some ball, and you take a closed rectifiable curve in BAR, then the integral of f on that curve will be 0.
Sir, I have a doubt.
Yes.
Sir, how alpha equals to R1?
So class, you just now, okay, don't worry. Now you forget all this. This was just intermediate calculations. So 1 upon alpha is equal to 1 upon R1. I think it means that alpha is same as R1. Yes or no? This is basic algebra.
Yes, sir.
No issue. No issue. Okay. So class, it was a nice implication of the theorem. And now class, I am going to just as a last item of today's class, and before I close this section, we are going to finish this section. This was section number 2 of chapter 4. I am going to take a problem. That's a very nice problem. Oh my God, I am to take score results. Shit. Okay, class, no problem. Okay, class. Class, 2 more consequences. One is this corollary that if f from G to C is analytic, class, take a note that everywhere G is taken to be open is analytic and A is in G, then class, again this is a consequence of the theorem that fz is equal to an z minus a to the power n summation n is going from 0 to infinity for all those z which satisfy the condition mod z minus a is less than r, where class r is the distance of a from the boundary of G. Class, just to save time, I will be sending you its proof in notes. Don't worry. Maybe today itself I will mail you a notes. So basically, I mean, the result is self-explanatory. It again tells you about the existence of power series expansion for an analytic function. The only thing is that in this case, the author is trying to tell you that this time the domain where you can talk of this series is being defined with the help of this distance. one more corollary class. Very simple, though I have already explained it to you. That was for the analytic function, but you can similarly talk of uh, oh, sorry, yeah, this I have already done class. If this was actually the remark with which I started in the beginning.
सर
Yes.
सर ऊपर ऊपर
जी
कॉरोलरी में आपने सर आर इज इक्वल टू डिस्टेंस बिटवीन ए एंड डेल्टा जी
जी
सर डेल्टा जी व्हाट इज डेल्टा जी
oh sorry class, this is uh, boundary of G. I hope you know the boundary of a set. Do you know the boundary of a set? Actually, class, uh, uh, let me tell you that suppose class you have a metric space. Sorry, good question. No problem. I can understand it. Suppose class you have a metric space. For example, in our course, what is our metric space? Our metric space is the complex plane with usual metric, right class? So,
Yes, sir.
suppose you have a metric space and suppose you have some set A in capital X. Then class, a point small x in capital X is said to be a boundary point of the set A if class, if and only if class distance of x from A as well as distance of x from A complement is 0. So class, I think you can easily imagine this, that suppose you have a set x like this, you have a set A is this, and suppose now you have a point, this is A. Now suppose you have a point whose distance, and this is A complement, whose distance from A as well as A complement is 0, then where do you expect that point to be? Perhaps here, right? Right?
Yes, sir.
So class, boundary points are the points which are exposed to A as well as A complement. For example, when you say the boundary of your college, so boundary of your college means that is exposed to the college as well as to the outside the college. If you consider the boundary of the college, then the building of the college is interior of that set of the boundary. It means that is inside the boundary, and on the other side of the boundary is outside. Is that what you call as at any point outside the boundary will be an external point? This is exactly what we say, right? If you want to enter the college, then show your I card, isn't it? Right? And then
Yes, sir.
class, if you take the collection of all boundary point, then that is called as the boundary of the set. So boundary of set is nothing but collection of all the boundary points. I write boundary only, boundary points. Sorry, boundary points. Then it is the meaning of boundary class. Is this okay?
ओके सर थैंक यू
So what you do, you just locate those points whose distance from the set A as well as its complement is 0, and that collection is called as the boundary. Good enough. So this is the meaning of boundary, and usually the meaning of boundary it coincides with its literary meaning, जो कि boundary का मतलब usually होता है, right? Okay. So if f from G to C, so the explanation, a detailed explanation for this also I will be sending you in notes. So if f from G to C is analytic, then just today in the beginning I told you that then f is infinitely differentiable, right class? Infinitely differentiable. This I have already explained, but I will be sending you some details in notes as well. So class, with this, I think I should stop. In fact, I was intending to do one nice example. In fact, This is precisely problem 10 at page 75 of your book J.B. Conway. So I will be taking up this next time maybe, though next time I will be first starting with the content of the next section, and then at the last of my class, maybe when 5 or 7 minutes are left, I will be taking up this problem. It's a very nice problem, and it will give you a further more better understanding, a much better understanding of Cauchy's integral formula. So that's why I like this problem. So this I will take up next time. So I think it's enough for today. We can stop now.
सर एक बार स्क्रॉल डाउन करना.
G. Further,
No sir, thank you.
do you want to do you want to know something about boundary points or boundary? Some example? If you wish, I can.
Yes sir.
Okay.
Yes, sir.
For example, let us take. Okay, I mean, there are plenty of examples. Let us take this. Now, suppose our set is, let us say, in the beginning, I am taking a very nice set. Suppose we take the set A, right, class? So now what will be the boundary? Boundary is collection of boundary points. So let's try to identify the points. So now, class, you identify those points. Now you see how I understand the boundary points. You understand the boundary points like this. You identify the points, first of all, the very first step, the points which are at the frontier of both A and A complement. उसी को तो आप बाउंड्री कहते हो ना क्लास. हमारे देश की बाउंड्री है जैसे, तो हमारे देश की बाउंड्री पे जो लोग हैं, they are at the frontier of both India and Pakistan. Yes or no?
Yes, sir.
Yeah, A means India and A complement means Pakistan. It means the rest of the world, right? So now you see. So what you do, this is 0 to 1 open interval. Then this is 2 to 3. I mean, you can take plenty of examples, as many as you want. And this is the real line. Is this okay, class? Minus infinity to plus infinity, right? So now you look at those points. Now you can see that this whole is the complement of A. Yes or no, class?
Yes, sir.
Right. So now you look at those points which are at the frontier of, it means you just imagine if you stand there, then anybody from A as well as from A complement can fire on you, can shoot you. What are those points?
0, 1, 2.
3. That's it.
Yes.
Is that okay? So that is first guess. So the boundary points are 0, 1, 2, and 3. And in fact, let me tell you, they are the only boundary points because I know. And now you can check, class, that distance of 0 from A as well as distance of 0 from A complement will be 0. I hope you can check this because distance is defined with the help of infimum, right?
Yes, sir.
Likewise for other points. Is this okay?
Yes,
Yes, sir.
So boundary means the points which are at the frontier of that set and its complement. In fact, class, I mean, you can talk of as many examples as you want. And those who have done graduation from Delhi University, for them, this Shirali Vasudev's book is, they must be familiar of all this. Otherwise, you can go through this book. This is Metric Spaces by Shirali Vasudev. This is a book by Springer. In fact, you can take any standard book on metric spaces. Is this okay, class?
Yes, sir.
Yes sir.
So maybe we can stop now. Class, there is a very interesting fact about the boundary of any set. Let me tell you, whether a set is bounded, whether a set is closed or not, its boundary is always a closed set. Class, if you take a set A, just a minute. So there is a very interesting fact about the boundary of a set. Whether the given set is closed or not, but its boundary will always be closed. That's a very important fact. And class, in fact, if you have a general guess, if you say in the sense of a layman, a boundary will be meaningful only when it is closed. If it is open from somewhere, for example, if the compound wall of your college is broken from somewhere, can that serve as a purpose of boundary? Can that protect you? Because someone may get into your college from that portion.
Yes, sir, that won't serve.
So that's a very strong mathematical property of boundary, that boundary of a set is always closed, whether the set itself is closed or not. Anyways, just a minute, class, just let me take your attendance. Sorry. So class, next time I will be starting with talking about the zeros or roots of an analytic function. Just a minute. Okay, thank you, class. I have taken your attendance. Now we will connect tomorrow. Thank you, class.
Thank you, sir.
Thank you, sir.